5. So this is Bose gas. And as usual, we start with the ideal Bose gas. Which means no interactions. So as we discussed in the first lecture, the wave function of n indistinguishable particles being fully symmetrized characterize the system of bosons. So bosons are characterized by fully symmetric function depending on quantum numbers, and this is n1 factorial, n2 factorial, so on, divided by n factorial square root, sum over permutations, and we have a phi p1 psi 1, where p1 denotes how many particles are in the state 1 times phi pn psi n. And of course, sum over all I and I is equal to n. So we have quantum states. However, as I said, the specific of bosonic system contrast to Fermi system is that for given quantum state, there might be arbitrary number of particles which are characterized by the same set of quantum numbers. Therefore, considering free bosons, we derived the distribution function and p average bosonic. For simplicity, from now on I will consider bosons with a spin s equal to 0, because we know that connection between spin and statistic tells us that bosons are particles with integer spin, while fermions are particles with a half integer spin. So in order to avoid summation of spin projections, I will assume that spin equal to 0, and free particle means that there is only kinetic energy. Epsilon p is p squared over 2m. So we derived Bose distribution function, which is 1 over e to the power ep minus mu over temperature minus 1, and as usual, I will measure temperature in the units of energies, then Kb is equal to 1. So it reflects the fact that Np, the number of particles in a given quantum state characterized by quantum number, which is a momentum, can be 0, 1, 2, and so on and so forth. Yeah, good. So we looked at this Bose-Einstein distribution function, and we see that the average occupation number should be not negative for any states p. Since EP is non-negative, so NP should be non-negative also for p equal to 0. So NP equal to 0, bosons is equal to e to the power e minus mu over temperature minus 1. It should be positive. From this, we conclude that the chemical potential, since exponent should be larger than 1, then chemical potential is non-positive. So it is negative and 0. Let's first discuss thermodynamics the same way as we did it for ideal Fermi gas. So the density of particles, which is number of particles per unit volume, is equal to sum over all P and P boson, and let's see, 1 over body. And this is with the usual way. This is integral over dp 2 pi I h bar cube. We are dealing with 3 dimensions without losing generality. E to the power EP minus mu over temperature minus 1. So this equation actually defines us the chemical potential mu as the function of temperature and density. By solving this equation for any given temperature, fixing the density of our bosons, we can find the chemical potential. Okay, and as I said, the chemical potential is non-positive. Let's assume that for some temperature, which we are going to find, temperature equal to T node, chemical potential becomes 0. Let's find this temperature. Which means we plug in here T node and find a solution of equation chemical potential equal to 0. So density N over V is integral over dp over 2 pi h bar cube. And here we have e to the power epsilon p over temperature minus 1. I already put, sorry, T node. So as usual, we have ideal Bose gas. Nothing depends on direction. The system is isotropic. Therefore, instead of integrating over momentum, I can integrate over energy. So this is 4 pi. I integrate over all solid angles, 8 pi cube h bar cube. And here we have an integral p square dp and e to the power p square over 2m t node minus 1. So I would like to introduce the energy units. So this is P dp. So therefore I will divide by m and multiply by m. So this is P m d p square over 2m, and p is also square root over 2m p. So therefore the integral is 4 pi m square root over 2m divided by 8 pi cube h bar cube, integral from 0 to infinity, square root of epsilon d epsilon divided by e to the power epsilon over t node minus 1. Good. The last step which we are going to make is to make this integral dimensionless. Therefore, I divide it by t node to the power 3/2 and multiply it to t node to the power 3/2. I introduce the variable z, which is epsilon over t node, and as a result, I have n over v is equal to 4 pi m square root over 2m over 8 pi cube h bar cube, t node to the power 3/2, and the rest is integral from 0 to infinity z to the power 1/2 dz e to the power z minus 1. This is the number. So this integral is number expressed in terms of zeta function. So what we get by knowing this number, we get that you see that the density is proportional to the T node to the power 3/2. So we can write down that T node is the number, and I know this number by heart. This is 3.31 h squared over 2m n over v to the power 2/3. So we found that for three-dimensional Bose gas, the chemical potential is 0 at some temperature T node, and it is negative for temperatures larger than T node. So it behaves like that. There is a finite temperature. So the question is, what happens here? Is chemical potential reaching T node and then goes down being again negative, or it remains 0? Because it cannot be positive, as we have just discussed. And besides, if we formally, assuming that chemical potential is 0, apply this equation for the temperatures below T node, what we find is that the density for arbitrary temperature below than T node, we can write down that for temperatures below T node, n over v scales as T to the power 3/2. However, it's definitely nonsense, because we fix number of particles and the density remains a constant, while the erroneous equation which we have written down tells us that, on the other hand, the density goes to 0 with the temperature goes to 0. So what is wrong with all these arguments? And it's clear what is wrong. So if we look at this equation, let's estimate what happens with the states p equal to 0 when chemical potential goes to 0. When chemical potential goes to 0, we can expand the exponent. So NBP equal to 0 is approximately equal to E1 plus modulus mu over temperature, because chemical potential goes to 0 and temperature remains finite, minus 1 plus and so on and so forth. It's approximately equal to temperature divided by modulus of chemical potential. And if we take limit mu modulus mu goes to 0, we get that this number becomes very, very large. Which means that the number of particles occupying the state characterized by 0 energy becomes macroscopically large. And therefore, when we write down our equation n over v is sum 1 over volume, sum over p, n p Bose, which is correct, the way we transform it to integral is no more correct at temperatures below T node. So we need to write down separately the number of particles occupying state with energy equal to 0 plus sum over p not equal to 0 and p Bose. So this is correct equation. So what then happened below temperature T node is that there exist macroscopical number of bosons occupying the lowest energy state. And this phenomenon is called Bose-Einstein condensation. Or BC, with abbreviation originating from first letters of B, Bose, E, Einstein, and C, condensate. In the literature, the acronym is BC. Okay, so let's see physically how we can understand that. Let's introduce the Broglie wavelengths. So lambda de Broglie is h bar over momentum. I put sub-index t indicated that this is a characteristic momentum which depends on temperature. So instead of energy, we plug in temperature, and this is h bar divided by square root of 2mt. Okay? And let's see what happens if we plug in t equal to t naught. Then we see that in this situation this is capital N, which is the density. In this situation, if we plug it in, then the de Broglie wavelength is 1 over n to the power 1/3. Okay? Which is, since n is inversely proportional to the volume, it is the distance between particles. So we see, therefore, that at temperature equal to T naught, the de Broglie wavelength becomes comparable with interatomic distance in our ideal Bose gas. Because this is what inverse cubic root of the density tells us. So let's visualize this picture such a way that for temperature we say that de Broglie wavelengths characterize as the size of the wave package. So if temperature is large than T naught, then the de Broglie wavelength is smaller than interatomic distance. So we have, so this is lambda T. You remember that quantum mechanics tells us that there is a wave-particle dualism. So at the same time we can speak about states as particle and wave. So this is what particle-wave dualism tells us. This is also lambda T, and this is average distance between particles. So if T larger than T naught, the distance between particles is larger than lambda T. This is picture number 1. Picture number 2 tells us that if temperature is smaller than T naught, then the de Broglie wavelength is much larger than D. Which means that we have a giant matter wave, giant wave function, and we can characterize our quantum state by unique wave function corresponding to the wave with a huge wavelength. Therefore, T naught has a meaning as a crossover or as transition temperature of the order of T naught when the description of the Bose gas as a system of individual, identical, non-distinguishable particles fails, and below T naught we should characterize the Bose-Einstein condensed state in terms of giant matter wave. This is the same for those who are familiar as with the lasers. So we have our light coming from the bulb, which is characterized by many incoherent zugs of the waves with a different wavelengths, which is not monochromatic. However, the laser, which is light amplifier, produces a coherent monochromatic wave, which is giant matter wave in a sense. What I'm saying is that there are many similarities between Bose-Einstein condensation and lasing, which people use, and which is one of the very hot topic in nowadays physics. If we now say that for temperatures below T naught, systems start to condense on the lowest energy state, ground state. Again, when I use the term condensation, I don't mean a condensation in real space. The condensation in real space, this is what you see when water condenses on your cold surface. I'm saying that condensation has a meaning of appearing in macroscopic numbers of particles occupying the lowest energy state of the system. Okay? Good. Therefore, we can write down that the number of particles in the condensate is equal to total number of particles 1 minus T over T naught to the power 3/2 if temperature is below T naught. So if temperature equal to 0 for system of non-interacting bosons, all n particles will be in the condensate. Okay? What I said before related to the free bosons, again, quantum box or whatever cartoon you like to visualize, to use to visualize free particles characterized by kinetic energy P square of m. At the end of boson chapter, I will probably give you a lecture with a slide showing the experiments discovering Bose-Einstein condensation in ultra-cold gases, namely magneto-optic traps and optical lattices. And what is important is that for these experiments, which actually open a new direction, a new area of modern atomic and condensed metaphysics, we do not have condensate in free space. We have a trap. For example, this is a harmonic trap. And we have a quantization of levels. As you know, for harmonic trap, harmonic potential, the levels are equidistant. And when we discuss the Bose-Einstein condensation phenomena in the trap potential, in confining potential, almost everything what I said before is correct, except that the particles will condense on low energy state, which is state now with h bar omega trap times 1/2. This is 0-point motion. And the chemical potential now should be smaller than this value. So, and of course, the power law here will be different. So one of the problems which you will get in homework is to consider three-dimensional harmonic potential. So no interaction between particles, but existence of confining potential, and find the power law for the number of particles in the condensate, and also find the temperature of a transition to Bose-Einstein condensation state. Okay, good. The last remark which I would like to make before I come to discussion of thermodynamics is what happens when we reduce the dimensionality. So when we come to two-dimensional Bose gas, and we can do it, it's another quite popular topic of research. One can confine the Bose gas, say, on a chip, which means you have a film style structure where the thickness of the film is much smaller compared to two other dimensions. So this is how we can visualize the two-dimensional electron gas. And as you probably discussed with in a different lectures, and in particular with Professor Nersisyan, the theorem, which is known as Mermin-Wagner theorem, tells us that no long-range order is possible in the system in dimension 2 except at temperature equal to 0, and in dimension 1 for any temperature, which says that Bose-Einstein condensation, which is in fact phase transition in ideal system, cannot occur in the two-dimensional situation except temperature equal to 0. So if you solve equation for Bose-Einstein condensation temperature, T naught for two-dimensional case using the same spirit, and plot it, you will obtain that for two-dimensional case T naught is equal to 0, which is in full agreement with what I have said. However, while saying that the phase transition, this is a phase transition, one should understand it in a sense of Landau-Ehrenfest definition of the phase transition, which I hope you have discussed in the language in the lectures of Professor Nersisyan. To cut a long story short, our thermodynamic potentials, which characterize the thermodynamic behavior of the system, being in equilibrium, namely characterized by thermal equilibrium, we can define the temperature, and mechanical equilibrium, we define the chemical potential. So the thermodynamic potential are always continuous function at any temperature. But if we start to take derivatives of the thermodynamic potential, we realize for certain phase transitions, the second derivative, namely specific heat, has a jump, and therefore, since it's a second derivative of free energy, we are saying that this is a second order phase transition, where, as Professor Nersisyan explained you, the phase changes continuously, so the order appears in all system, which is then associated to spontaneous symmetry break. This is what we are going to discuss on the next lecture, starting with lecture number 2, having example of the interacting Bose gas, and we discuss superfluidity. However, for some system, it happens that the first derivative of thermodynamic potential, namely entropy, has a jump. It happens, for example, when you boil the water. You boil the water, the temperature remains constant, you pump energy into the system, and therefore the specific heat, which is related to derivative of entropy, actually is equal to infinity, which means the entropy has a jump. So since it's the first derivative of free energy, we are saying that this is the first order phase transition, which behaves completely different, contrast to second order phase transition. And again, if you have in mind the picture of boiling water, you see that what happens is the bubbles of the vapor appear inside water, they go up and they evaporate on the surface. So the essence of first order phase transition is in homogeneous situation, so you cannot have any more homogeneous order appearing in all system. You have a nucleus like bubble which appear in the system, and at the end of the day when your water completely evaporated, you have a vapor. So this is water-vapor transition. The same way ice is formed in the river, as you probably see it. There are pieces of ice which form on the surface of the water, and then with your low down temperature further and further, and the surface completely covered by ice, and then you go down, and at the end of the day, all water or liquid you have is frozen. So this is an example of first order phase transition. Having said that, I would like to give you an exercise. It's not part of homework. You can consider this ideal system. We compute now the energy. This is what I do. I compute for you equation of state. However, start taking derivative of energies, and please see which derivative of energy has a jump. My hint is that neither first nor second. And then with this spirit, you will identify what kind of the order of phase transition you have in the system. I will now start computing thermodynamics. However, you may ask me, I'm telling you that there is a phase transition occurring in ideal non-interacting system. In principle, we used to the fact that the phase transition appearing due to some interaction, and this is what we see for superfluidity. Namely, we consider system of weakly interacting bosons. However, what I told you in the first half an hour of this lecture, that for bosonic system, we do have phase transition, which is characterized by appearance of giant wave function, condensing your state into the ground state. And if there is anything of that sort in thermodynamic system. So this is another question which is very legitimate to ask, and the answer is yes. There is also a phase transition in ideal non-interacting theory system. However, for having that phase transition, one needs to go to the lattice. And again, for those who are curious and to learn something new, I'm not going to discuss it now. This phase transition, which is called Lucia's transition, is associated with the change of the shape of cyclotron orbit, or on the vulgaris language, people sometimes say that the shape of Fermi surface changed such a way that it converts from closed Fermi surface to open Fermi surface, which is a bit, as I said, vulgaris language. It's better to speak in terms of cyclotron orbits, which become open after being closed. And this is topological phase transition because it is related to the change of topology. So those who are interested to learn more, please Google and read the literature, and you might be surprised that in the spirit of Landau and Ehrenfest classification, this thermionic phase transition in free fermion system on the lattice has a fractional order. It's phase transition over 2.5 order. Good. So, thermodynamics. Or any questions? Thermodynamics, energy. So we compute energy of the system. It's sum over P, epsilon P, and P bosons average. Right? Here, for energy, we don't need to separate the energy of the states characterized by the momentum equal to 0, because if the momentum equal to 0, the energy is automatic 0. So here, I don't have any macroscopic number. I can adopt with the summation of all states P. So then, this is a volume, so nothing bad with transforming our summation of the quantum states to the integration dp over 2m, 2 pi h bar cube. We have p squared over 2m and boson. So this is the energy. Again, since from very beginning I consider they're spinless particles, there is no extra summation, which accounts for degeneracy because of the spin quantum number. With the same way, I will write it down as the square root over 2 m square root over 2 m energy, m the energy, and there is a 4 pi, and I will also assume that temperature is below T naught in this equation, therefore the chemical potential is 0. So what we have here is volume, and this is 4 pi square root over 2 m divided by 8 pi cube h bar cube, and I have integral from 0 to infinity. I have energy times energy to the power 1/2 the energy, and e to the power energy over temperature minus 1. So the total power is 3/2. Therefore, I can write it down as V times temperature to the power 5/2. This is how I make it dimensionless. It's 4 pi square root over 2 m divided by 8 pi cube h bar cube. And here we have an integral from 0 to infinity, z to the power 5/2, sorry, z to the power 3/2, dz e to the power z minus 1. So this is again a number. Because the integral doesn't depend on anything, I made it dimensionless. So I would not care about this number. I will just write it down as some gamma times volume times temperature to the power 5. Okay? So, then CV, which is specific heat per unit volume, I will use the capital C for extensive quantity and small c for the quantity per unit volume. So this is 1 over volume d energy over d temperature at constant volume. So this is gamma times 5/2 times temperature 3/2. So this is energy, this is 5/2, energy per unit volume divided by temperature. Okay? So, on the other hand, CV is temperature d entropy over d temperature. Therefore, we can write down that the entropy, this is entropy from this equation. This is integral from 0 to temperature, CV over as a function of t prime divided by t prime dt prime. This is how I expressed the entropy solving this equation. So if I plug in, so this is integral from 0 to temperature 5/2 temperature to the power 3/2 divided by the temperature t prime dt prime. This is temperature to the power 1/2. Therefore, the integral can be taken very easily to 1/5 divided by 2/3, and there is a gamma here, of course, gamma temperature to the power 3/2. So this is 5/3 gamma temperature to the power 3/2. Okay? So the free energy F is E minus T dot S. Therefore, the free energy is gamma volume temperature to the power 5/2 minus 5/3 gamma volume temperature to the power 5/2, right? So this is minus 2/3 gamma volume temperature to the power 5. So this is entropy per unit volume. This is total entropy. Yeah. The pressure in the system, pressure of the system, pressure is minus d free energy over d volume at temperature and chemical potential constant. So this is then 2/3 gamma temperature to the 5/2. Okay? And if I multiply this equation by the volume, I get P dot V is equal to 2/3 gamma volume temperature to the power 5/2. This is 5/2, 2/3 the energy. So this is the So this is the equation of states. I did not derive it for you for system of non-interacting fermions. I asked you to do it yourself by computing the thermodynamic potential omega, which I can also do it for bosons. It's even simpler. But if you did it correctly, you have find the same quantum equation of states, that P dot V is equal to 2/3 of energy. And if we plug in classical limit that the energy is equal to 3/2 kBT times n, we get Mendeleev-Clapeyron equation, classical Mendeleev-Clapeyron equation, that P dot V is equal to kBT times n. Okay? However, there is something spectacular in this equation. Namely, if we look at this equation, this one, what we see is that the pressure doesn't depend at all of the volume, contrast to what we had for fermions. Besides, the pressure is proportional to the temperature times temperature to the power 3/2, and as we see that the temperature to the power 3/2 is amount of non-condensate fraction of the states at given temperature. I denote it as n prime, so this is temperature times n prime. So for ideal system at 0 temperature, n prime goes to 0, and the pressure goes to 0. However, what we see, again correctly, is that the pressure is produced by those states which are out of condensate, because these states are characterized by non-zero momentum. So all the states which are in condensate do not contribute to pressure at all, because the momentum of this state is 0. Okay. Good. Any questions? If not, in the remaining 45 minutes, I'm going to turn the interaction on and discuss the system of weakly interacting bosons from the point of view of very important equation, which is called Gross-Pitayevsky equation, which is sort of nonlinear Schrödinger equation. This is equation which is characterizing the behavior of system, quantum mechanical behavior of system of interacting particles. And by deriving this equation, this is what I'm going to do in a very simple way for you in the remaining 45 minutes, and finding the low-lying excitations by solving the linearized version of this equation. We will come to some conclusion, and the lecture on Friday will actually be devoted to completely different way to derive the spectrum of weakly interacting bosons. So, from now on, I will turn on the interaction. Let me write down the Hamiltonian of the interacting bosons as integral over dr prime, and I will write it in the language of first quantized states. I will write it as a psi operator dagger depending on r prime, so minus nabla over 2m psi h bar is equal to 1 r prime. This is kinetic energy. Then I have a particles in a trap Vr prime. Doesn't matter, but psi dagger r prime Vr prime psi r prime. This is something what can characterize me external potential. Plus, I will assume that my particles are sort of hard balls which interact only when they contact each other. So D is typical size of the wave function characterizing bosons, and in order to do it, I will also assume that, as I said, the interaction occurs only when the particles collide. So the potential of interaction N1 minus R2, which of course depends on the momentum, is G times delta function R1 minus R2. So it's pointless particles. Of course, I can assume the delta function approximating it by some Lorentzian or Gaussian wave packet. But what I'm saying that the situation when particle interacts only when collide is applicable when the main distance between particles r bar, which is inversely proportional to the density to the power 1/3. Again, this is a three-dimensional case. So I'm assuming that r bar is much larger than the size of the ball, which means that the density times d cube is much smaller than 1. So this is a gas approximation. The low density approximation, if you remember last time we considered electron subject to Coulomb interaction. Coulomb interaction is very long range interaction, and as we discussed, the Coulomb gas becomes ideal in the opposite limit because the kinetic energy competes with the potential energy, and potential energy is very long range. Here, the system is characterized by extremely short range interaction. So, what I'm saying, if you want to adopt D, so it will be like D divided by L1 minus R prime square plus D square, and I take limit D goes to 0. Good. So I will then write it down G over 2 because typically second quantized term looks like 1/2 psi R1 psi R2 psi R2 psi R1 U R1 minus R. But since I have a delta function, I write down that this is G half psi R prime psi R prime psi R prime psi. Okay? And since I'm going to work with a grand canonical ensemble, so a fixed chemical potential but not number of particles, with your permission, I will write that the H, which is H minus mu n, which is equal to this, and what I need to subtract is minus mu psi r prime. And this is all operators. So this is interaction, and this is mu n. Okay, good. And what I'm going to do is to write down equation minus I, which is the Heisenberg equation of motion. As you see, psi are operators. I d psi over dt is equal to commutator over h bar and psi. Okay? So this is equation which I'm going to derive with a curly h defined in the following way, when I assume that this is a short range or contact short range or contact interaction of almost point-like particles being in a regime where the gas parameter, and this is a gas parameter, is very small. This is a gas approximation. And finally, we will connect this potential with a so-called scattering lens, and we also discuss what happens if we have long-range interaction. So we have a system of bosons. So the operators psi and psi prime taken at the very same moment of time, because this is a Heisenberg picture, satisfy commutation relation. Psi r prime t psi dagger r prime t minus psi dagger r prime t psi r prime t is equal to function delta function r minus r prime. Okay? So let me now compute the right hand side of the equation. Namely, I start computing commutators. So the commutator between H kinetic and psi RT is equal to integral over dr prime, and here I have psi dagger r prime minus nabla over 2m psi r prime psi r minus psi r psi r prime dagger minus nabla over 2m psi r prime. Okay? So this is the left hand side is a commutator, and as a kinetic energy, so this is H kinetic. So what I can do, psi and psi commute. So if I replace psi dagger by psi, I will get 0 in right hand side. So I can interchange now and write psi r prime. So this is the first step. The second step, since nabla, which is differential operator, is written in a space r prime, it doesn't act on a psi r. So I will write this as a psi dagger r prime psi r minus nabla over 2m psi r prime. So now with these operators, I can interchange them, writing that this is psi r dagger prime using this. However, what I will get is minus delta function r minus r prime. As a result, the first term will be exactly cancelled by the second one, and what I get is minus integral over dr prime, delta function r minus r prime, psi, minus nabla over 2m, psi r prime. So therefore, since delta function eliminates me the integral, it's minus minus some plus nabla over 2m acting on a psi r. Okay? So this is 1, this is 2, this is 3, this is 4. So we see that structure 2 and 4 is alike. So therefore, I will compute 2 plus 4 in a single shot. So this is HV plus H mu psi R T. Are you with me? Are you following me? Because I am doing very simple calculations, but you need to understand the logics, why I'm doing that, and what we are going to get at the end. As I said, at the end, we are going to simplify the right-hand side, and since it's a Heisenberg equation of motion flow operator, we will write it in the sense of getting the equation of motion for interacting particles. So what I have here is dr prime. So this is psi r prime dagger v r prime minus mu psi r prime psi r minus psi r prime dagger v r prime minus mu psi r prime. Again, I can interchange this psi r prime, and what remains is psi r prime dagger psi r. I can write it down as a psi r prime minus delta function r minus r prime. Therefore, the first term will be cancelled exactly by the second term in the commutator, and what remains is dr prime. I have with a sign minus delta function r minus r prime, and I have v r prime minus mu acting by psi r prime. So this is minus vr minus mu times psi r. Okay? Now I am in a position to compute 3. To compute 3, which is commutator of Hg and psi r t, and this is the interacting term, this is g over 2 integral over dr prime, and I have psi dagger r prime, psi dagger r prime, psi r prime, psi r prime, psi r, minus psi r, psi I prime dagger, psi I prime dagger, psi r prime, psi r prime. So now I have to compute it and take psi r through all ordering of psi r prime in order to get something which cancels me out by the second term, and I need to compute what remains. So clearly I can interchange twice without any problem. So this is g over 2 integral over dr prime, and I have psi r prime dagger, psi r prime dagger, psi r prime, psi r prime, minus psi r prime dagger, psi I prime dagger, psi r prime, psi r prime. So this was the first and innocent step. Now, by commuting these two, I write that this is psi r psi I prime dagger minus delta function r minus r prime. So the integral with a minus delta function will give me minus g over 2 actually psi r dagger psi r, and then in the remaining part I need to commute this annihilation operator with this creation operator, and I use the same commutation relations with the delta function, and I get yet another g half. So this is minus g, then remaining term will be cancelled, and this is psi modulus squared. Okay, so now I'm in a position to combine everything. Minus I d psi over dt is equal to minus minus nabla over 2m psi minus Vr minus mu psi minus g psi modulus squared psi. Or I can multiply everything by minus 1, both left hand side and right hand side of my equation, and what I will get is I d psi over dt is equal to minus nabla square over 2m plus Vr minus mu plus g modulus psi square acting on epsilon. So this equation, first of all, resembles very much the single particle quantum mechanics equation. This is what we get here, which is a linear, since we do have a superposition principle in quantum mechanics. However, the equation which I derived for you is nonlinear differential equation, because it is nonlinear in terms of your many body wave function. So the equation, as I said, is called Gross-Pitayevsky equation, and this is a sort of the non-linear Schrödinger equation. And non-linearity appears due to the interaction, since we have a system of, it's not single particle, this is a many body quantum mechanics where there is pairwise interaction between particles. Okay? And this non-linear Schrödinger equation plays very important role in the many phenomena associated with them. Soliton formation, light propagation in wires, fibers, and so on and so forth. Since it's nonlinear, it allows some non-trivial and also topologically non-trivial solutions. We are not about discussing that. We are going to solve very, very simple problem now, based on the fact that the Bose system can condense into the ground state, and see what are the consequences for that in the system of interacting bosons, contrast to non-interaction case, which I discussed in some details before. Any questions? Do we discuss any interacting quantum mechanics, many body quantum mechanics in advanced quantum mechanics course? Are you familiar with this nonlinear Schrödinger equation or Gross-Pitayevsky equation?
No.
So it appears for you for the test. Okay. Suppose we do have Bose-Einstein condensation in the system. And for the moment, for everything else which I'm going to say from now on, I will assume that there is no trap potential VR is equal to 0. So I will drop this term, although by the derivation which I presented to you, the equation is generally derived for the external potential and accounts for existence of this external potential. Second, I will assume that the ideal, so to say, bosonic system goes through the Bose-Einstein condensation transition, in which, as we said, the macroscopic number of states collapse into the ground state of the problem, which is state with a momentum equal to 0. In this sense, I can write down, since psi modulus square is n, so you remember that n is then would be integral over dr prime psi modulus square r prime, then, and I have a macroscopic number of state, I can write down that my psi operator has very large constant part associated with the condensation of macroscopic number of particles into the ground state, plus I assume that there are some monochromatic fluctuations, so the remaining part of the wave function, which is a function of r t, can be written down as monochromatic chi r minus omega t plus d star e to the power minus I k r minus omega t. So I have two monochromatic waves, and I will be looking for solution of my Gross-Pitayevsky equation in the absence of confining potential in this form. Okay? So kinetic energy minus nabla over 2m acting on psi r t. Oh, sorry. Before doing that, let's write what I d over dt psi r t is. So the first constant term, this is a uniform condensate. So we have all states, as I said, which are sitting at p equal to 0 state. Having a delta function at momentum p equal to 0 means that this is uniform in real space, right? We take Fourier transform. So therefore only these two terms actually subject to time derivative. So this is I times minus I omega a e to the power. And with your permission, I will call, in order to use a shorthand notation, I will write this as exponent e plus, and I will denote this exponent as e minus. Because I don't want to write down every time all arguments. So I times minus I omega a e plus I times I omega b star e minus, which is omega a e plus minus omega b star e minus. So at the end of the day, I will write also the right-hand side of this equation, linearize it, assuming that n is sufficiently large number. I keep only certain power of n, and therefore, since these two exponents are linear independent, I will compare coefficients in front of e plus and n minus, and as a result get a system of two coupled linear equations, which I'm going to solve. And solution of this linear equation will give me some condition for determinant. And this is how I'm going to find the dependence of omega as a function of the wave vector. which will give me the spectrum of excitations in the system. This is what I'm going to do. And let me now proceed. Is it clear?
Yes.
The strategy, what I'm going to do, and let me proceed with the calculation. So, minus nabla over 2m, this is k squared over 2m, a times e plus b times e minus. Now, with a term without exponents, if I plug it in here, so those terms which, let me write it down here, this is 0 times 1 times 0 times square root of a density. In sense times 1 because it doesn't contain any exponent. So with a term which doesn't contain any exponent with 0, I will write it as a mu minus mu plus g psi modulus square root of n is equal to 0. So this equation, although it looks absolutely primitive and trivial, is actually a very deep equation which connects the chemical potential with the interacting constant. So this is a chemical potential which is a product of the interaction constant times the density of your uniform condensate. On the lecture on Friday, we will see that one can derive this equation in much more complicated way, and the equation itself is called Pines-Huygens theorem. From this Gross-Pitayevsky equation, this is a trivial, simple derivation. So you understand what I did. I plugged square root of n here and there, and I derived this equation. Now, let's write down the nonlinear term. So g times psi modulus square psi, this is g times square root of n plus a e plus b star e minus multiply square root of n plus a dagger e minus plus b e plus. This is what is psi modulus square. I multiply psi by psi complex conjugated, and yet another square root of n plus a e plus b star e minus. So let's open first this bracket. So this is g times n plus square root of n. I have a plus b. So this square root of n a and this square root of n b e plus square root of n a dagger plus b dagger e minus. So I keep term linear in n and square root of n. And then there are some terms which are proportional to a modulus square, b modulus square, and a b plus ba. All these terms do not contain n at all. And n is macroscopically large number. Therefore, I will omit this term. And what remains is square root of n plus a e plus b star e minus. So I already kept term in order of n and in the order of square root of n. So what I have is g, and this is n to the power 3/2 plus n a plus b e plus n a dagger a star plus b star e minus. This is, I multiply this and this term by this one. Yes, and then I need to multiply this term. So plus n a e plus n B star E minus. And that's it. I'm not going to keep terms of the order of square root of n anymore. I keep only n3½ and n. So what then remains? Omega A E plus minus omega B star E minus is equal to K square over 2m A E plus plus B star E minus. This is a kinetic energy term. Plus minus mu plus Gn. This is this term. So let me write this. Mu square root of n plus A E plus plus B star E minus. So this is this term plus G n square root of n plus n A plus B E plus n A star plus B star E minus plus n A E plus n B star E minus. So I want everything. So now from this condition, this term and this term cancels out, right? And also this term and this term cancels out. So sorry, not this. This term and this term cancels out. And what remains are these two terms. Therefore, I will collect all terms in front of E plus. This is this term and this term, and all terms in front of E minus. This is this term and that term, and write it down as two equations. So omega A is equal to K squared over 2m A plus Gn A plus B. So these are coefficients in front of the exponents I, K, R minus omega t. The second equation is minus omega B star is equal to K squared over 2m B star plus Gn A star plus B star. Okay? With this equation, with your permission, since I'm going to solve two linear equations in terms of A and B and find the condition, I will take a complex conjugation. So I will delete star here. And this is a system of two linear equations. So A, I will take everything to the right hand side. Omega minus K squared over 2m minus Gn times A minus Gn times B is equal to 0. And I will take G NA plus omega plus K square over 2M plus GN beam is equal to 0. Okay, so I will write it this way and this way. So now the system of two linear equation has a solution if determinant is equal to 0, right? So this is determinant of the matrix. I will write it as determinant of some matrix M is equal to 0, which is omega minus K square over 2M plus Gn multiplied by omega plus K square over 2M plus Gn plus Gn square is equal to 0, or omega square minus K square over 2M plus Gn square plus Gn square is equal to 0. You see, I didn't do any mistake, and since I did not, omega square is equal to, I put everything into the right hand side, and this is a difference of squares, and the difference of squares is K square over 2M plus Gn minus Gn times K square over 2M plus Gn plus Gn, and therefore omega is equal to square root over K square over M times Gn. This is this term times this term plus K square over 2M square. This condition of 0 of the determinant gives me K dependence of my omega of spectrum of the excitations in the system subject to interaction. So if we plot this curve, so you see I got this spectrum almost for nothing in half an hour or so. Next time, because it's pedagogical way, I will spend a bit more time, but use completely different way, which is not at all related to Gross-Pitayevsky equation. But if we plot omega k as a function of k, what we see that for small k, this is linear in omega. So we have c dot k, and then we have k squared over 2m as a spectrum of ideal Bose gas. So the message is where c is square root over g times m. So what we see in the system of interacting bosons, the dispersion or energy dependence on a k vector changes its character. So instead of being dispersion of non-interacting particles, which is k squared over 2m, it now becomes a sound like. So we have gapless mode, which Professor Nersison explained you in literature called Goldstone mode. This Goldstone mode is associated with spontaneous breaking of certain continuous symmetry in the system characterized by short-range interaction. We have a sound in the system. And the velocity of sound is proportional to the square root of interaction on one hand side and square root of the condensate density on the second side. So if your system becomes non-interacting, g is equal to 0, sound mode disappears. If you are not in the condensate, sound mode disappears either. However, the existence of this sound-like excitations in the system leads to very important phenomena called superfluidity. So the system of bosons, interacting bosons, weakly interacting bosons, being in a regime of boson-state condensate, can flow through the capillaries without any friction. Friction means without emitting any phonons. And this phenomena was experimentally observed, and Nobel Prize was given for experimental observation of this phenomena, and the phenomena is called superfluidity. It's closely related to phenomena of superconductivity, which is possibility to superconduct current or to conduct current by certain metals below certain temperature without any friction, without any resistance. And all of this is related to certain, now it's second order phase transition. One can show that this, and we do it, that the transition to the superfluid state is second order phase transition, but we will also see that ideal Bose gas does not produce any superfluidity. For superfluidity, one needs to make it interacting. Okay, that's all for today. Any questions? Just want to see that I didn't forget anything. Okay. No questions. Then, problem to think about it at home. Suppose that instead of the short-range contact interaction, we can plug in G as a Coulomb interaction 4 pi e square over k square. In the next lecture, I will derive you the spectrum without any assumption about short range of interaction. And if we do so, and if we plug it in here, we will get that the spectrum of the charged Bose gas with the boson-state condensation is then characterized by gapped, because k squared will be cancelled out. This is a Coulomb interaction, and what we will get here is 4 pi e square n divided by m. This is a plasmon frequency of the charged Bose gas, and plasmons, as I told you last time, are associated with the density, the fluctuations of the density of charge. So the plasmons are excitations as function of density of charge. Please think how one can describe this plasmon excitation in the Bose gas using the technique which I gave you in the last lecture in application to thermodynamic system. Okay. If no more questions, Fridays we consider the Bose gas, and next Monday you will have a first tutorial discussing thermodynamics of fermions, calculation of specific heat, and rules to compute integrals with the Fermi distribution function at final temperature. Good.